guys, how are you? Today's lesson will speak about the ideal gas and what we need to go through it and to understand it is how to identify the meaning of the ideal gas. Secondly, relate the microscopic gas law with the ideal gas. And the third part we have to go through it is how to solve problems about the ideal gas. First of all, we already got from previous about the Avogadro's number and also the gases law that we have to go for another relation comes here because of the many circumstances that comes which are not often being satisfied for understanding the gases relation. So we got here to understand that the relation that comes together between the three of them, the pressure, volume, and temperature, be counted like this. Pressure 1 V1 over T1 equals P2 V2 over T2. This is the overall relation between the three objectives that we are speaking about the gas and how they are related together from the Boyle's, Charles, and the Gay-Lussac. Today's we have to understand that if we can find that the gases being in a certain amount of temperature and pressure to be constant, and if we added some amount of the other gas, that means that the mass of this gas will be increasing, which means also the volume will be increasing though. So that's why we can say here the relation can be different. Also, if the volume and temperature of this gas become constant and you add a special amount of the gas, which means the mass will increase and also the pressure will be increased. So if you fix two things of them, a volume with a temperature, the pressure will increase, or pressure and temperature would be fixed, that means the volume must be increased. This is happen when you have an added amount of these gas. The relation would be turned to be P1 V1 over M1 T1 equals for you P2 V2 over M2 T2. We said that if we are gathering all of this information together about the gases to be written in a certain amount of the changes that happens, which means that we have to go through another part that is related for these gases changes, which is the added mass and also the increasing amount for the material like pressure or volume can be counted as a constant to give it as an R, which will be taken with a certain number. We will get it later. And the relation would tell itself directly when there's a experimental observation happening over this gas to be more generalized, and the relation will be changed to be P1 V1 over N1 T1 equals P2 V2 over N2 T2. What is the N? The N is the number of the moles. So if P1 V1 over N1 T1, it's give you a constant amount which also equals the same amount of the change that happened for P2 V2 over N2 T2, which means it leads us to understand a new term which we call the ideal gas. The ideal gas here, it's not real, it's something theoretical that happened for modeling a gas. It helps you to understand the behavior for other gases, and we have that the gas or the ideal gas here have the following assumptions, which we can see that it's happening to understand the other gases. The first rule here, or the circumstances that is related to the ideal gas, that the molecules are point particles, which they part are neglectable for their volume. Also, the molecules they obey the law of mechanics. The third part is that there are no forces between the molecules except when the molecules collide together. The duration of this collision is negligible for the particles of the gas compared to the time between the collisions, and also the collisions of the molecules with each other and with the container walls are elastic. And the third and the last part is the molecules have a range of speeds and move randomly. All of these assumptions for the ideal gas is not related to normal gases. It's different from each part of them. We can find here that the ideal gas here, unlike the real gases, they cannot be liquefied or solidified. The real gas here may be approximated by the ideal gas when the density is low. Last part is when you state the gases here, it's being determined when we know the values of the pressure, volume, temperature, number of moles, and those parameters are related together to understand the ideal gas. And you can find here that the equation for the ideal gas says that P multiplied by V equals NR multiplied by T. The R here is a constant, as we said before, a universal gas constant, which equals 8.314. And the P is the pressure, the V is volume, T is the temperature, and N is the number of the moles. You can find down here the units for each one. You have to understand that the volume within meter power to 3, which means when he gave you in the problems, you have to change the meter centimeters into meters, or millimeters to meters, whatever the number he gives to you, you have to change it to normal meter. Also, the temperature is not measured with the Celsius, it's over here with the Kelvin. And the pressure here must be an atmospheric pressure, which equals for you 101.3 kilopascal. For any thermodynamic process here, it involves the movement from one state to another, and this could involve the changing for P or V or even T. We can see here for any thermodynamics process that happen to any gas, they have some terms that leads to a type of understanding. We can find here the first part is named the isothermal process, which means there's a constant temperature process happening. If he says that it's an isolated, which means that the number of moles is constant. If he said it's isothermal, the T is constant. Isobaric, which means the P is constant, and isochoric, which means the V is constant. You can find here that in this problem that he says in an ideal gas that is being kept in a container for fixed volume and temperature for 30 degrees Celsius and the pressure for 6 atmosphere. The gas is heated at a constant volume. The temperature changes to be 330 degrees Celsius. Find for the yourself that the new pressure that happened to the gas. So the pressure was 6 when the temperature was 30, and the temperature right now is 330, and we need to go for the new pressure. To get the new pressure here, we have to use this relation PV equals an RT, that he has to change it from Celsius to be in a Kelvin. You add the 30 to the 273, initial and final. And the volume is constant, it doesn't change at all. So you can remove here the V with the V, initial with the final, or 1 with the 2. And also the nRT is constant, the number of moles is constant, and also the R is a constant, so you can remove them, which gives you at the end the P final, which is P2 equals P1 T2 over T1. So you multiply it and they get the numbers, and then at the end you get the pressure, which gives you 12 atmospheric pressure. Another question here said that in a fixed quantity of the gas, the volume is 3 multiplied by 10 power to minus 3 meter power to 3. The pressure is 3 multiplied by 10 power to 5 Pascal, and also the temperature is 300 Kelvin. It expands to a volume, so here the volume has changed to be 4 multiplied by 10 minus to 3, and the pressure becomes 6, which is also changes. This is P2. We have here V1, P1, T1, and also we have here V2, P2, and we are missing T2. Number of moles at this in those parts, he said a fixed quantity of the gas, which means number of moles is constant, so N1 equals N2. And here we can find the relation being said as P1 V1 over N1 T1 equals P2 V2 over N2 T2. So you multiply the numbers together, and then at the end you can get the final temperature, which gives you 800 Kelvin. Go for the questions 1, 2, 3, 4, and submit your answer if you don't mind, please, and also 5. Thank you.